Substitution is a super powerful tool, and it allows us to find antiderivatives for more complicated functions. For example, here we're looking for the antiderivative of sine t divided by cosine cubed t. We don't have a rule for that, so we're going to do our best to use substitution to clean it up in a way that we can integrate the function using one of our rules that we already know. So we'll start by picking u to be some function of t, and we want to find the innermost function. Now, looking at what we have, there's a few choices that we could make, and it's easy to not know which one to make when you first learn substitution, but with practice, it becomes like an art, and you know exactly which function you need to pick. So I'm going to go through each of the possibilities, and we'll eliminate which ones aren't very useful. Maybe we let u be sine t, the numerator. Or maybe we let u be cosine cubed t, the denominator. Or maybe we let u be cosine t, the thing that's inside of the power of 3 in the denominator. So at first glance, any one of these looks like an inside function, but when we go through the process of finding du dt, only one of these is going to work out as far as replacing terms in our integral. If we picked u to be sine t, then we would need to have cosine t dt to be able to replace the differential with du. And maybe you think we have that, but we really don't. If we replaced the numerator with u, the denominator would be cosine cubed. That's kind of the same thing as u times 1 over cosine cubed. And that is not the same thing as cosine times dt. This is 1 over cosine cubed dt. This u sub is not the business because it doesn't allow us to replace dt with an appropriate du. So let's move on to our next choice. Picking cosine cubed t, we find du to be negative 3 cosine squared t sine t dt. And we definitely don't have this necessarily. Let's take a look. If we replace cosine cubed, our denominator, with u, then we're left with sine t over u dt. And our differential that we found for du does have sine t dt, but it's missing the cosine squared. And that's not an easy alteration to make. So this one also not the business. Hopefully this last one will work. We picked u to be cosine t. Then du is negative sine t dt. Looking at our integral, if we replace the cosine in the denominator with u, our denominator becomes u cubed. The numerator was sine t, and we had dt. And would you look at that? We almost have this exactly, sine t dt. We do have a small alteration of a negative. We can fix that just like we did the last time. We can multiply through by a negative so that we'll have negative du is equal to sine t dt. Then our integral will become, instead of sine t over u cubed, I'm going to write that as 1 over u cubed. And instead of dt, I'm going to pull out my sine t dt and replace that with the equivalent, a negative du. And that negative really represents a multiple of negative 1, so we could write this as negative 1 over u cubed, or negative u to the negative 3 du. And in fact, we could even move that negative outside of our integral since it's a constant multiple of 1. We don't have to write the 1, we can just write a negative there. And then we integrate this using our power rule. U to the negative 3 becomes u to the negative 2 because we've added 1 to the exponent, which means we'll divide by negative 2. Don't forget there was a negative multiplying out to the front, so we will multiply that there. And since there are no bounds on our integral, we have an indefinite integral, which requires a plus c. We're almost done there. We have negative u to the negative 2 over negative 2. Let's simplify the double negative so that we have a positive. And if we'd like, we can rewrite u to the negative 2 as 1 over u squared. So we can have 1 over 2 u squared plus c. And then our final step would be to replace u in terms of t again. So remember that we said u is equal to cosine t. So our antiderivative really looks like 1 over 2 cosine t squared plus c. And that's our final antiderivative. Example 5.34 shows us another integral that requires u substitution. Again, we might have some trouble picking out what the u is, but you can go through each of the possibilities and decide which one works best for replacing our x's with terms in u. Let's go ahead and use u as x minus 1. That's the function inside of the square root function in the denominator. So then du would become 1 times dx. And then when we go to replace our integral, we know that the denominator is going to become the square root of u. We have x dx left, and our du differential does not have a factor of x in it. So we could just replace dx with du, that's fine. But it's not okay to still have an x inside of our integral. Remember, we need to replace everything with terms of u. Now in this case, we can do it because we picked u to be a linear function of x, which means that we can invert this. We can look at it as u equals x minus 1, and we can solve for x. Add 1 to both sides, so we get u plus 1 equals x, and we can take the x out of the numerator and replace it with a u plus 1. Now everything inside of our integral is written in terms of u, and we're good to go. To finish this off, we do need to do some alteration. Just using algebra, we're going to rewrite the integrand as u over root u plus 1 over root u. We'll simplify each one of these, so the first fraction is going to become u to the 1/2. The second fraction will be u to the negative 1/2. Using our power rules, u to the 1/2 becomes u to the 3/2 divided by 3/2. And then u to the negative 1/2 becomes u to the positive 1/2 divided by positive 1/2. And since we're working with an indefinite integral, we'll be sure to include the plus c. We can clean this up just a tad. Let's replace our division of fractions with a multiple of the reciprocal. So we'll have 2/3 u to the 3/2 plus 2 times u to the 1/2, and of course carry over the plus c. And then our last step is to replace u with the equivalent in terms of x. So we'll have 2/3, not 2/2, 2/3 times x minus 1 to the 3/2 plus 2 times x minus 1 to the 1/2 plus c.